Hi guys, Mr. J here. Today we are going to start our last vodcast of this unit, and that's on what we call IMFs, also known as Intermolecular Forces. These are the forces that exist between molecules. So let's go ahead and get started. Previous to this, the only types of forces that we've really talked about a lot are what we call our intramolecular forces, okay, or intramolecular bonding. These are forces that are found within a molecule. These are what are responsible for making up our chemical bonds, okay? They keep the atoms bonded to each other. So we're talking about our ionic bonds, our covalent bonds. And what we see is these are relatively strong bonds, especially when we're going to compare them to intermolecular bonds here in just a minute. These are relatively hard to break compared to our intermolecular bonds. Now these intermolecular, I'm going to call them bonds, are actually forces. They're not a chemical bond like we see in ionic and covalent bonds, but they're a force between different molecules. It's what holds molecules together. So you got to keep intermolecular and intramolecular separate from each other. Way I remember, I had a student a couple of years ago give me this analogy. She thought about the international community, or the relations between different countries. So inter is between, intra is within. So that's how I always remember. Maybe it's a little bit easier for you as well. Okay, so these intermolecular forces are what holds molecules to each other. Maybe at one time or another you did the experiment where you saw how many drops of water you can put on a penny, and slowly what you see is that water builds up, it begins to round out. Well, the reason those water molecules are able to do that is they're being attracted to each other through what we call these intermolecular forces. Okay, and as I said, it's a physical force. It's not a chemical bond like we see with covalent and ionic bonding. It's between molecules, not within. Okay, and as I said on the previous slide, these intermolecular forces are much weaker than the intramolecular forces. Okay, but why do we care about them? Well, these forces are going to determine a lot of the physical properties of a bond. Okay, things like what's the boiling point, the melting point, vapor pressures, viscosity, which is how likely things are to flow. Okay, so those are all determined by the intermolecular force, and those are all physical properties, not chemical properties. If we look here, we have hydrochloric acid, HCl. The hydrogen and chlorine here together are held together by an intramolecular bond. Okay, but between the different molecules, we see an intermolecular, which is relatively weak compared to the intramolecular. So we're talking about these bonds here, the intermolecular, that holds different molecules to each other. Now today we're going to talk about 4 different types of these IMFs, intermolecular forces. The first one occurs when we have some sort of ion present. We call these ion dipole forces. The next 3 occur with neutral molecules. So a molecule, covalent, right? Okay, the 3 types are what we call the London dispersion forces, the dipole-dipole forces, and then finally a special type of dipole-dipole forces which we call hydrogen bond forces. If we look at the relative strength of these last 3 here, what we see is the London dispersion forces are weakest, and the hydrogen bonding is the strongest. That's what we see in the water when we talked about that penny lab, why those water molecules are able to kind of bubble up like they do, so to speak, because our hydrogen is relatively strong in these intermolecular forces. Together, these last 3, the London dipole-dipole, are also known as van der Waals forces, so you may hear that term from time to time as well. Okay, let's talk about the ion dipole. So as the name kind of implies, you have to have an ion, which, right, a charged atom, and then you have to dipole. If you remember dipoles is just another name for a polar molecule. Okay, so these ion dipole exist between an ion and a partial charge in the end of a polar molecule. Okay, we can see it in here. So we have a cation, positive charge, right, is being attracted to the negative side of a dipole or polar molecule. The other one here, we see a negative anion being attracted to the positive side of a polar molecule. Now remember, with polar molecules, overall their charge is neutral, but they have a slightly positive side, slightly negative side as well. Okay, so they're important solutions of ions, and what we see is the strength of these forces, of these ion dipole forces, what makes it possible for ionic substances to dissolve in a polar solvents, and we'll see that on the next slide here. But here's kind of an example here. We have water, and we have a solution of KCl. We know when we put it in water, it'll disassociate, and so we see the negative side of our water molecule being attracted to the positive potassium ion, and then the hydrogen side, which has that slight positive charge, being attracted to the negative side of chlorine. If we look at here's sodium chloride in water, right? Here's our polar molecule, right? Water. Remember, hydrogen's positive, the red oxygen negative, so it's going to be attracted to the sodium that pulls those off, and then the hydrogen end ends up pulling off the chlorine. So that's what we see happen in ion dipoles. Getting into our second group that occurs with non-polar molecules. First one is the London dispersion forces, also known as either dispersion forces or LDFs. Okay, we see these forming when there's a momentary shift in what we call the electron density, or where the most electrons are located within a molecule. Okay, those shift. When they shift, they create what we call an instantaneous dipole moment. Okay, and an instantaneous dipole moment means that for just a split second in time, that non-polar molecule takes on polar characteristics. One side is really has a more negative charge, has more electrons, which means the other side is missing an electron, so it becomes more positive. Okay, so and the thing to remember is this is just instantaneous. It'll go and shift back to normal, so it's a relatively weak one. Okay, and what we see is when one of these substances shifts, forms this instantaneous dipole, it can influence nearby molecules, causing them to shift as well. Okay, as I said, they're also known as dispersion forces. It's the weakest of all the IMFs. Okay, and it's the LDFs, what we see, are present in all molecules. Okay, one of the questions AP asks oftentimes is what type of forces, intermolecular forces, are present? The answer always should start with LDFs for molecules because they're always present in all molecules. Now, there could be other type of forces as well, but LDFs are always present, and it's the only type of force that's present in nonpolar molecules. So here we go. We got an isolated molecule here. The electrons are equally dispersed. Okay, if we see, we get this little distortion here. When it's distorted, we get kind of the distortions going this way, so we get a little more negative on this side, a positive over on this side, and then it can distort the neighboring. We get the negative being drawn towards the positive. And between these, we get this IMF, or this intermolecular force, this London dispersion force forming between them. It's a relatively weak force, okay, so it's easily disrupted once these go back to their normal shape, but we can see it here. So London dispersion forces are caused by an instantaneous dipole, which causes this electrostatic attraction between the molecules. As we said, the reason this occurs is because the electrons in the orbitals are free to move around, and when they move around, they kind of distort themselves. And when they distort themselves, they form this instantaneous dipole, this temporary polar molecule, and then we get attraction between opposite ends of it. What we look at, or one way to kind of predict this, is we look at the polarizability of these different nonpolar molecules. And what polarizability is just the ease in which this charge distribution, or this electron density in a molecule, can be distorted, or it measures how easily electrons can move about their orbitals. Okay, or we can say another way to say is the tendency of an electron cloud to distort. In general, what we see is this ability to distort, or this polarizability, increases with the size of the orbital. So as we get larger orbitals, okay, we get more of this. Why? Because as we get more orbitals, we're getting greater distance between our electrons and our nucleus, our protons, and then the electrons are able to move about more freely. Okay, they're less strongly attracted to the nucleus, they're less bound by it. Another thing that we can look at affects these forces is the size of the molecule, as determined by its molar masses. So the strength of these dispersion forces tends to increase with the molecular weight, because as I said, as we're adding molecular weight, we're probably getting more orbitals, which then makes it easier to distort. So increased molar mass will also give us a stronger LDF. Okay, so as we said, larger atoms have larger electron clouds, which are then easier to polarize. Our next type of van der Waals force is a dipole-dipole. Remember, dipole means a polar molecule. One where if we look over here, we have a positive side and a negative side. Overall, though, this molecule is going to be neutral. Remember, they're only partial charges when we talk about them. So dipole-dipole interactions are formed when we have molecules that are permanent dipoles or polar molecules that are electrostatically attracted to each other. We get the positive end being attracted to negative end, just like we talked about in LDFs, except this is a permanent dipole. So they're not going to shift back to normal as easily as, or their normal is to polar, I should say. And so the positive end of one molecule is attracted to the negative end of another. Okay? And just kind of like LDF, the strength of this attraction increases with the total number of electrons. The more electrons that we have, the more polar the molecule becomes, and we have a stronger attraction there. Our third type of van der Waals force is what we call hydrogen bonding. Hydrogen bonding is just a specific type of dipole-dipole. Okay, it exists between a hydrogen atom and a polar bond and an unshared pair of electrons in a nearby atom. Well, those atoms that it has to be with are three specific ones. It's going to be fluorine, nitrogen, and oxygen, or you can remember by the mnemonic PHONE, fluorine, oxygen, nitrogen. Okay, so we get HF bonds, HO bonds, or HN bonds occurring between different molecules. So here is, we can see here is NH3. Here's a hydrogen. This nitrogen has an unpaired bond there, so unpaired electrons, or non-bonded one to say. So we get this attraction between the hydrogen and this unpaired and forms a hydrogen bond. And these are our strongest of the IMFs. Okay, they're relatively strong. It's like we talked about with water. It gives water a lot of its unique properties. We can see another example here. Here is water. Okay, we just talked about. Here is our intramolecular bonds, our covalent bonds. Now we have a hydrogen here and an unbonded pair of electrons here. So between the hydrogen and unbonded pair, we have this hydrogen bond that forms. Here's a couple other examples. Here's water bottles. Here's the NH3. Here's water and NH3. So we can see that bond. It has to be between hydrogen, either nitrogen, oxygen, and fluorine. It goes to the unbonded pair in there. All right, so how do we determine the type of IMF that exists? Like I said, one question that AP will often ask you is list all the types of IMFs that occur. Well, understand, first of all, it can be more than one type that are affected it. Okay, so the first thing we have to do is draw the Lewis structure. Hopefully you're feeling pretty good about that. Once we have the Lewis structure, we can determine the shape of it and the symmetry of that molecule. Once we know that, that lets us know if it's polar. Does it have a dipole moment? Okay. Once we know that, well, how do we determine that if it's polar or nonpolar? What we're going to do is look at the central atom. Okay. If the central atom has no lone pairs and has all the same type of atoms attached to it, it's going to be a non-polar molecule. Now, if that central atom has no lone pairs, but it has different types of atoms attached to it, then it's going to be polar. And the third thing we look at, if the central atom has lone pairs of electrons with it, it's going to be a polar molecule as well. So pretty simple rules to look at. Okay, so once we know if there's a dipole moment or not, if it's polar, then we can start describing. If there's no polar molecule, it's going to be an LDF for sure. Okay. If there is a polar molecule, it's going to be LDF first as our weakest. Then it's going to either be dipole-dipole or hydrogen bonding are going to be our predominant one, our dominant force existing in there. So remember, our hydrogen bonding is between hydrogen and fluorine, hydrogen and oxygen, hydrogen and nitrogen, with the hydrogen going to the unbonding with the, or not bonding, but creating a force with the unpaired electron or unbonded electrons there. And as we said earlier, more than one type of IMF can exist in any molecule. So make sure if the question asks, you list all those types. All molecules are going to have the LDFs. Okay. Now, nonpolar, that's the only ones they're going to have. If it's polar, it could be IMF, it could be a LDF, it could be a dipole-dipole, it could be hydrogen bonding, so it's more than one. So let's look at an example here. CH4, methane. If we look at the Lewis structure for that, we see a central atom carbon, and we see 4 of the same atoms to catch it. So that is an example of a nonpolar. Our next one, SO2. If we draw out the Lewis structure for this, first thing I see is that I have a lone pair on here. Knowing that I have a lone pair, the predominant one that I'm going to have is going to be the dipole-dipole. Why isn't it hydrogen 2? Well, this is not nitrogen, oxygen, or fluorine. H2O, okay? There we got our lone pair, but there's our oxygen, right? That's one of them, one of 3 molecules that leads to hydrogen bonding, so we're going to have hydrogen bonding as our predominant one there. CCl4, that's going to be a lot like our CH4 here, right? No lone pair, so once again it's nonpolar, LDF. Here's one, CH2Cl2. If we draw this one out, what we see is there's no lone pairs, but on this central atom we have chlorine here and hydrogen, so they're different atoms attached to it, so that means it's going to be a polar molecule. Okay, in that case we're talking dipole-dipole. Alright guys, so here what I'd like to do, I'm going to give you a couple examples here. I want you to pause the video and see if you can figure it out on your own. So carbon dioxide, OCS, H2, and HF. Go ahead and pause and come back once you've drawn the Lewis structure and then determine what type of IMF it's going to have. Alright, here's carbon dioxide, same element on each side, no lone pairs, so we're talking nonpolar, so it's got to be an LDF. OCS here, okay, if we look at here, once again, no lone pairs, but we have different atoms on either side, so this is, it's not symmetrical, okay, so it's going to be a polar molecule. Let's get dipole-dipole. H2, right, looks something like this, okay, it's attached to the same thing, so it's nonpolar LDF. HF, okay, we have hydrogen connected to fluorine here. Fluorine's got those unpaired electrons, okay, so we can actually get hydrogen bonding going on with this one. So once you get the hang of it, it's not too hard to do. Okay, let's look at this last question here. Which molecule is capable of forming a stronger intermolecular force? Explain your choice. So pause this, think about it, come back. All right, so let's see what's going on. We got N2, right? It's going to be bonded to itself, so that's going to be an LDF. H2O, we already talked about, that's a hydrogen bond. We know that hydrogen bonding is a lot stronger than the N2. So the water has a stronger intermolecular force because it exhibits hydrogen bonding, whereas N2 only exhibits the LDF forces. Here's a nice little flow chart you may want to look at, kind of figuring out, taking you through, what type of force exists. So you may want to copy this one down if you don't have it already. All right, today guys, we talked about the 4 types of intermolecular forces: the ion dipole, the London dispersion forces, the dipole-dipole, and the hydrogen dispersion, hydrogen bond. We talked about how to identify what type of bond exists between different molecules. First, you have to draw a Lewis structure, figure out if it's polar or nonpolar, and then go from there. All right, guys, if you have any questions, please drop me an email, and we can talk about it later. Till then, guys, take care.